So, welcome to the stream, guys. And today we'll be solving, or rather explaining the solutions to MindStormer 2020. Remember? Let's go to the first question. Hmm. When things slow down a bit, Dr. Rupo likes to do puzzles. The puzzle states that if you are provided an integer n, first of all, you have to find the numbers whose digits add up to equal to that number. Each of the digits are to be added with 1. Now you have to find the number of digits happen to be the minimum and print its sum of digits. So what task is, like, we are given a number, let's say s. We are given a number, let's say s. S is equal to something, let's say a1, a2, a3. This is in string format, and let's say the sum of these numbers is equal to x. And then we need to find all numbers whose sum of digits is equal to x, and then we add 1 to all those numbers, and the new number, let's say we get x naught. For every such x we get another x naught. Then we need to print the sum of digits of that x naught, that is minimum. So the statement seems complicated, but it's really easy. So what you can do is, if let's say sum of digits is equal to x, then you can place 9 9 9 and then a number here, remainder. Let's say the remainder after dividing it by is y, then this will be y here, and 9999, and when you add 1 here, this will reduce to y plus 1, then all will become 0. So simply the solution will be, calculate the remainder, x over remainder, then add 1 to it. And if the remainder is 9, remainder will never be 9, like it's 9, then that's it. So that's basically the first problem. Let me show you the code. This is what I did here. I calculated the sum of all the digits, then calculated remainder, and then printed remainder plus. Yeah, so this was the first question. Hardware. So this was the first question, really easy. Now the second question. You are given an array of size n. You need to find the integers that end with integer k. So this is really easy as well. You just need to go through each element of the array and check if that number ends with k. You need to print the index. So I don't think this requires an explanation. I'll just show the code. Just go through all the elements, and if the last digit is equal to k, just print the index. It's really easy. I'm gonna skip this one. Now comes the king's army. Now in this question, I will explain you what you need to do. You need to split your army into 3 troops, such that all the troops this side have power less than m, all the troops in this area have power greater than equal to m but less than l, and all the troops on this side has power greater than equal to l. If it is possible, you need to find the maximum sum of such LMM that is possible. Uh, you can you need to find the maximum sum of such L plus M. all the these here should be less than m, here greater than equal to m, less than l, and here greater than equal to l. So the very first observation that we can take is that the array needs to be sorted first. So we firstly sort the array, and now these three strengths should be equal. So now here should be n by 3, here should be index 2 n by 3, here is all the rest of the indexes. So if these two elements are equal, or these two elements are equal, we can say that answer is equal to -1, because all the elements here should be less than m and here should be greater than equal to m. But if these two elements are equal, we can never satisfy the condition that this is less than m, this is greater than equal to m. So answer, if these two elements are ever equal, is equal to -1. So if these two elements are equal, the answer will be -1. And in the other case, now if these elements are not equal, we now know that this element will have a fixed value. Let's say this is equal to a and this is equal to b, because we know these are not equal. This is equal to c and this is equal to d. Now we know these are not equal, and now here we know that the sum is always greater than or equal to m, and we need to maximize l plus m. So we need to take maximum m and maximum l. So we know that b is greater than equal to m, b is greater than equal to m, and b is less than l, and here d is greater than or equal to l. So we can just take the ended indices and print their sum, and this will be the solution. Here is the first index b, because we know this is greater than equal to m, so all these indices are less than m. So if we take b equal to m, this will be the maximum such index such that a will be less than m, and these are less than l, so d is such maximum l such that c is less than d. Let me draw that. Here is a, here is b, here is c, this is less than m, this is greater than equal to m, here is greater than, and we need to maximize l plus m. So we can choose any element between a plus 1, a plus 2 equal to b, 2b equal to m. But if we choose b plus 1 equal to m, then this element will fall into this category and the size will increase, and then this will no longer be equal halves. So we can choose any value of m from a plus 1, a plus 2 to b, and we need to maximize, so we always choose p. Similarly, we can choose any value of l from c plus 1, c plus 2 to equal d, but if we choose d plus 1, then this element will fall into the second category and the size will not be equal, so we can only choose from c plus 1 to d. So we will always choose d here, and the answer will be b and d. So this is what I did. Here is n plus n by 3 to n by 3, and we then add this value. So this is n by 3 to n by 3, and then I just print m and n. So this was this. Now comes price distribution. Price distribution, club is going to have 10 candy boxes. N is less than equal to 10 the power 3, let's say 10 the power 5. And there are k students, k is equal to 10 the power n, as an equal to 10 the power n, and 9. These are the number of students. And club needs to distribute these candies among these students, and chocolate boxes have around ai is less than 10 the power 9. So in the end, all the students will have k candies. So sorry, in let's say in end all the students have x equal candies, and this is the maximum number of candies. Now in these types of questions, like, we need to find the optimal solution. An optimal solution, like maximum or minimum of something, is generally found using binary search. And a very sorry for that. So a very important observation right here is, like, if we can distribute x equal candies among all children, we can also distribute x minus 1 candies, x minus 2 candies, and x minus 3, and so on till 0 candies. So if x is a solution, x minus 1 is also a solution, x minus 2 is also a solution, up to 0. But this is the maximum number of candies, so x plus 1 will never be a solution. So we can see a graph of something like yes divided by x, and then no. We can see there are two equal halves here, yes and no. So we can do a binary search on this. So what we do is we can least amount of candies we can distribute is 0. Maximum amount of candies we can distribute is 10 the power 9. So we apply binary search here, calculate middle. Then if we check if middle satisfies the constraints, if mid is an answer, we update answer equal to mid, and then we look another answer. If we know that mid is an answer, so this falls on yes. So we know there is an answer on left side, so now we go to the right side to find a more optimal answer. So we update low equal to mid plus 1. But if mid is not an answer, then we know we are in the no half. So we know all the values on the right side are also no. So we now go to the left side to find an answer. So then we update high equal to mid minus 1. So this is the basic binary search. This is the code. This is the check function that check if n is the answer. Here low is equal to 0, high is equal to max n is equal to 10 to the power 9 plus 1. And then we check middle. If this is the answer is equal to mid, and then we go to the right side. If this is not the answer, we go to the left side to look for an answer. And then we print the answer. Yep, binary search. So was it? Now this question, chocolate collection, the test cases are wrong. And the test cases, this is the test case, but the output is 0 0 0. So the test cases are wrong. That's why I got 16. So this is a standard question of difference arrays. So if you have not studied difference arrays, you can also implement segment tree with lazy propagation. Lazy propagation, yeah. So you need to implement segment tree with lazy propagation. But this is not really required. You can use lazy propagation to update in m log n time, and then use each query in log n time, so answer will be O of q log n. This should also work, but segment trees are not really required for this. You can solve this using difference arrays. So what difference arrays are, you can look it up online. What is difference array? This is difference array range of get query in O1. So range of or let's say you cannot search for, yeah, segment tree will not work because then you need to sort the segment tree. I don't know if that's possible to sort the segment tree. But I think this is the only solution for this. So difference arrays, what difference arrays are, first of all the elements are 0. Now and the only you can read the like blog posts online how to implement difference arrays, but the main idea is you always keep track of first element. Just keep track of this element and you are good to go. So now when we update a segment L and R, let's say we update this segment by +1. So now we keep track of the difference between these elements. So if we update this by 1, the difference between these elements is increased. So we increment here +1. So we now know the difference between these elements is 1, but the difference element between these elements is still 0. So we need not do anything here. And then the difference between these elements now decreased by 1. So we update -1 here because this array increased. The difference between these elements decreased by 1. So this element's array is increased by +1 and this is increased by -1. So for every range update from L to R, you update a difference of L is equal to plus equal to 1, and then difference of R +1 is minus equal to 1. Now you implement for all the M updates, and in the end you will get a difference array of something like this, whatever. So now it is important to keep track of the first element, because if you don't know the first element you will not be able to make the whole array again. So now we have a difference array. Let's say first element, I don't know what first element is. I have keep it in another variable first differently, and now we have a variable, we have here 3, but this 3 in difference array means is that this element is 3 times greater than the first element, and if there is -2, this element is 2 times smaller than the second element, and so on. So now we know the relative values of adjacent variables. So now if we know first, we can build the whole array. So now if I know the first that I stored before, let's say I know first is equal to 5, then I know this is 3 greater than 5, so this value will be 8. This is 2 less than this value, so this should be 6, and so on. We can now build the whole array. Now my resultant array I know is this, and now I have 2 queries, and Q is very large, so I need to answer each query in O of 1 or O of log n, and the answer is to find elements greater than this. So this can be done using binary search. So we sort the resultant array and then implement binary search or lower bound, and then answer each query in log n. So this will be the solution for question. Let me show you the code. So here we have v, n and m. First, this is my first variable that will keep track of the first element. Here is q, c and nm, and here is my v array, and this is my difference array. And so if L is equal to 1, I know the first element is being updated. So if I know L is equal to 1, I know the first element is being updated right now, and I need to keep track of the first element. So I update my first. Next I update the difference. I increase the difference here and decrease the difference here. So this is what I do right here. And then I know the first element of my array resultant is equal to first, and I kept track of. Then I go on building resultant of I. Like I know this element resultant of I know this element difference. This element should be this element plus my difference. So resultant of I is equal to resultant of I minus 1 plus v of this my difference. Now I know the resultant array. I sort the resultant array. Then I input q queries, lower bound. This is basically binary search, and then output the answer. Really basic stuff. And now Tom's Pride. This is basically pattern recognition. You need to What you need to do here is you need to make up 3 to 4 test cases on by your hand and just test them. Like if we have A1, A2, A3, we need to do operation on this m times, and then for each value of m, let's say x goes from 0 to m minus 1. Then in each turn we need to change z of x mod n equal to z of x mod n xor z of n minus 1 minus x mod n. So we apply this operation, we get a1 xor a3, a2, a3, a1 xor a3, 0, a3, a1 xor a3, 0, a1, a3, 0, a1, a3, 0, a1, a3, 0, a1 xor a3, a3, a1, 0, a1 xor a3, a1, a1 xor a3, a1, 0. So we again get the same array after 1, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 and 9 operations. So after 3 n operations, you get the same array again. So this is basically pattern recognition. And so if the n is odd, you know that this element will always become 0 after greater than equal to n by 2 operations. So this is the only corner case that you need to worry about. Else you can take mod 3n, and you know you will get the same array again, and then manually implement 3n operation. So code here is 3n, then I take the remainder, and if m is greater than equal to 2 and n is odd, I know that this element will always be 0 from now on, so I update this to 0. And now for I equal to 0 and remainder, while this remainder I keep updating. I manually do up to 3n operations, and and n is equal to 10 to the power 4, so 3n operations should not take that much. But m is very large, so it was important to reduce n. So this was it, and then I manually implement index I mod n and index n minus 1 minus index, this is the I mod n, and this was this operation, and then I just output the array. So this was it, pretty standard stuff. And the first question was kind of tricky, second was very easy, third so fourth one was a good example of binary search, fifth one was a good example of difference array, and this one was just ad hoc pattern recognition. You know that you cannot apply and the part value operation, so there must be a pattern or some stuff that's or any special kind of pattern that you need to find out. And so this was it. Bye bye.